I'm thrilled to introduce our first speaker, which is Casey Honnibal. And Casey's talk is entitled Molecular Water on the Sunlit Lunar Surface, Detection of the 6 Micron HOH Fundamental with the Sophia Airborne Observatory. So go ahead, Casey.
Can you see my screen and hear me?
Yes, we can.
All right, perfect. So we are at 1:35, so I'll go ahead and get started. So as Ariel said, I'm Casey Honnibal, and I'm going to be presenting the first ever detection of molecular water on the moon using 6 microns and the Sophia Airborne Observatory. So I'm going to start with some background. For many decades, the moon was thought to be dry, but beginning in 2008, evidence of lunar hydration began to emerge. And Sal et al. 2008 measured high water contents from pyroclastic deposits returned by Apollo. Then in 2009, 3 spacecraft measured a 3 micron absorption feature, which is attributed to hydroxyl and possibly molecular water. And then most recently, UV observations show a diurnal signal in the water-ice band ratio, possibly indicating molecular water on the moon. Now, while these observations show that the moon is not dry, the 3 micron and UV observations have not been able to distinguish between hydroxyl and molecular water. And that's because of the ambiguity in the 3 micron band and lack of laboratory studies. So the 3 micron band is created by the symmetric and asymmetric stretch of the OH bond, and both hydroxyl and molecular water exhibit this 3 micron band. This plot here shows the different forms of molecular water and hydroxyl at 3 microns, and as we can see, they are all very similar. Further complicating this 3 micron band is that the hydroxyl attached to different metal cations can mimic the shape of molecular water. And so currently the band shape and center of hydroxyl attached to different metal cations cannot be predicted, and separating water from hydroxyl is difficult at 3 microns. In the UV, the water-ice band ratio has been used to detect ice deposits at permanently shadowed regions. But on the sunlit moon, it is unknown what causes these water-ice band ratios to vary diurnally. Hendricks et al. 2019 assumes that adsorbed water spectrally behaves like water ice in the UV, but there's no lab data to confirm this, and hydroxyl cannot be ruled out just yet. Therefore, there has been no definitive detection of molecular water on the sunlit moon. So new methods are needed for its detection, and fortunately, molecular water shows a fundamental vibration frequency at 6 microns, which is explicitly due to molecular water without contamination from hydroxyl. The 6 micron band is strong and narrow and well suited for the detection, and if you can see my mouse, it is shown right here in this spectrum. So while this method is new to remote sensing, it is not new for the detection of water in geologic thin section samples and has been used since 1962. It has even been pointed out in the literature that observations of the moon at 6 microns could prove the existence of water. The 6 micron band has, however, been observed in remote measurements of samples and planetary bodies. Apollo samples measured at RELAB and meteorite samples measured at APL exhibit both a 3 and 6 micron band shown here in A and B. And from spacecraft, a 6 micron band has even been observed on Mars, shown here in C, and on asteroids, shown here in D. What's interesting is that the 6 micron feature on Mars has even been mapped, as shown in this image on the bottom. These examples show that if molecular water is present on the moon, it should exhibit a 6 micron band. But currently, there are no spacecraft capable of making 6 micron observations of the lunar surface, and from ground-based telescopes, the atmosphere is completely opaque. This plot shows the atmospheric transmission from Mauna Kea Observatory here in blue, and as we can see at 6 microns, there is no signal available to measure. However, the higher the observatory, the more the atmosphere opens up, and this allows us to use the Stratospheric Observatory for Infrared Astronomy, SOFIA, to look at the moon at 6 microns. SOFIA flies at an altitude of about 14 kilometers, which is 99.9% above atmospheric water vapor, opening up the 6 micron region as shown by the green line up here. Using the forecast instrument on SOFIA that operates from 5 to 8 microns, we have made the first observations of the moon at 6 microns looking for molecular water. Our first flight on Sophia was on August 30th, 2018, and we collected 12 frames of data with 248 spectra each. We observed 2 different locations, a Mare reference location shown here by these white lines, which indicate the slit location of the forecast instrument, and we also observed the Clavius crater region down at the high southern latitudes, shown down here. So results from these observations are shown in this plot, and these spectra are from each of the Clavius region observations, showing the maximum and minimum spectra that reported molecular water abundances. And so you can see that there is a strong and prominent 6-micron emission band in each of these frames of data that we collected at Clavius. These bands are about 2% in strength, and we attribute them to molecular water. And this is the first unambiguous detection of molecular water on the sunlit moon. Now, just to prove that this band that we're observing on the moon is due to molecular water, we compared our lunar 6-micron band properties to other observations and to literature values of the HOH band centers. So this histogram here shows the distribution of literature band centers from Falk 1984 in red, and overlaid we put the lunar band centers in blue. And we can see that the lunar 6-micron band centers all fall within the range of the cited band centers from Falk 1984. Now, if we take a look at this bottom plot, we see that we compare the moon lunar spectrum to meteorite spectra and to water-bearing glasses. And when we look at the lunar spectrum in red and compare it to meteorite spectrum in black, we see that they are similar in shape, center, and width. But when we look at and compare the moon to the water-bearing glasses, we see that it is broader and shifted to lower wavelengths. These results, however, indicate that we are actually detecting molecular water on the moon at 6 microns. So next, we estimated the abundance of water present. And so to do this, we used the strength of the 6-micron band, which correlates to absolute water content, which is commonly used to measure water in thin sections. We are using the strength of the band to estimate water abundances in remote sensing data, which has not yet been done. So we use the water-bearing glasses with known abundances of water that feature both a 3 and 6 micron emission band or absorption band to derive an empirical relationship between band depth and abundance of water. The empirical relationship is shown on the bottom plot. So we estimate that about 100 to 400 ppm of water is present in the Clavius crater region with a mean of 250 ppm. This histogram here shows the abundance of water for each spectrum in the Clavius region, and the plot next to it is showing the abundance of water as a function of latitude measured by Sophia in black, and also the total water abundance measured at 3 microns by the Moon Mineralogy Mapper in red. And when I say total water, I mean the sum of hydroxyl plus molecular water at 3 microns. So the abundances we measure with Sophia all fall within 1 sigma of the measured M cube abundances. And the latitude trend we observe with Sophia is due to the location that we observed, with some of our observations passing through Tycho crater ejecta. So the lower latitude, thank you. The lower latitude observations were in Tycho ejecta, while the higher latitude observations were not. So this latitude trend is probably localized and likely not a global phenomenon. Lastly, we wanted to infer where the water might be stored on the lunar surface. So there are a few places it can be, but I'm only going to focus on 2. And the 2 are chemisorbed on grain surfaces or sequestered into impact glasses. At the latitude and temperature of our 6 micron observations, models suggest that only 3 ppm of water can be chemisorbed on the grains. So this implies that the water we are observing with Sophia is actually not on the surface of the grains, but stored within the grains, the impact grains themselves. And we estimate that 300 to 1300 ppm of water is confined within impact glasses. These results are consistent with water being produced from pre-existing hydroxyl during micrometeorite impact. So in conclusion, we have made the first direct detection of molecular water on the sunlit moon using Sophia forecast 6 micron measurements. We estimate abundances in the hundreds, in the range of hundreds, and we find that most of the water is likely stored within impact classes. And the trend we observe with latitude is a local phenomenon and not a global phenomenon. So in the future, we plan to continue this work by continuing observations of the moon with Sophia, with over 20 hours of observing time coming up. And we plan to map water on the moon and compare our 6 micron and to compare 6 microns and 3 microns to each other, looking at the differences in diurnal variations. We will also be investigating the presence of molecular water at pyroclastic deposits to provide better estimates of hydroxyl versus molecular water, and which provides better constraints on and to inform us about future missions to the moon regarding potential resources. And that concludes my talk. Thank you.
Thank you, Casey. That's really exciting work. So reminder, we have lots of questions and excitement in the chat. So I'm just going to go in order of people that raise their hand. Jen, if you want to go ahead and unmute yourself.
Sure. Yeah, that was really fascinating. I just had a quick question. If you could explain how or why you focused on the Clavius region, and if you know where you'll be able to map on your upcoming Sophia flights.
So we chose the Clavius region because we wanted to pick something that was very obvious to find in the Sophia guider images, because these observations had never been done before. Clavius was very obvious, and it was at high southern latitudes, which meant we had a higher chance of detecting molecular water than we did at lower latitudes.
Okay, and I think we have time for one more quick question. Pam Clark, do you want to unmute yourself? Okay.
I'm trying to unmute myself. Wait, can you hear me?
There we go.
Sorry, that was difficult. Yes, I'm just very interesting observations, and the separating OH from H2O is crucial. So when you're talking about water associated with pyroclastics, what's the nature of that water? You're talking bound, or are you talking absorbed water, or some combination of the two? Can you tell the difference? Thank you.
We probably won't be able to tell the difference between adsorbed and bound, but we believe that the pyroclastic water would be from internal water from the moon when it was like erupted during a volcanic event. So okay. In the future, maybe we'll be able to distinguish adsorbed from internal, but we would need models to base that off of.
Okay, thank you.
Thanks so much, Casey.